Well, hello people in calculus land. Today is our first look at section 5.6 in your calculus book, which is related rates. So a couple of things that you're going to need to know about this. When we say related rates, what we mean is we're taking derivatives with respect to time. So whatever it is, if it's an area formula, then we're going to figure out dA dt. If it's a distance, for example, a distance in the x direction, we're going to say dx dt. And in order to do that, we're going to have to use our implicit differentiation skills that we learned about a chapter back at this point. So we're going to brush up. This is implicit differentiation. Of course, implicit differentiation is really just the chain rule. So at the base of all of this is we're using a chain rule to find derivatives with respect to time. All right, let's get to our problem. And you encounter a zombie, a fast one, and it is in the cramped back alleys of downtown. You have a bit of a head start on the zombie, so you're able to turn the corner on a perpendicular alley. Currently, you are 0.1 miles east of an intersection and running east at 13 miles per hour. So you're pretty fast. You're really fast. I think that's kind of unhumanly fast, if I remember correctly. The zombie is 0.1 miles north of the intersection and running south at 9 miles per hour. So again, that zombie is unnaturally fast. Everything here seems to be unnaturally fast, but that's okay. We're just solving problems. So at what rate is the distance between you and the zombie increasing? This is the classic related rates problem. So like we said before, we're going to take derivatives with respect to time. So here's our little bit of review here. All derivatives are with respect to time, and the chain rule, if necessary, for all is going to be used for any variable that is not t. So for example, in this formula, pi r squared, the derivative of a is equal to the derivative of pi r squared. And so what is the derivative of pi r squared? Well, the derivative of pi is constant. You don't have to worry about that. Now the derivative of r squared, and the derivative of anything squared is 2 times that anything. So 2 times r multiplied by the derivative of r, which is dr dt. We'll see more of that later. Let's zoom in the number 2 so we can get a really good look at it. Over here, we're taking the derivative of volume equals 1/3 pi r squared h. I believe that is the volume of a cone. So the first thing to do is take the derivative of volume. So dv dt is the derivative of volume with respect to time. And over on the right side of the equality, we have ourselves a 1/3 pi r squared h. Okay, 1/3 pi is just constant. R squared h is a product. So that's what you're going to see here. We've got the 1/3 pi for everything here, 1/3 pi. Then we're going to take a derivative of r squared. What is the derivative of r squared? What is the derivative of anything squared? It's 2 times that whatever is being squared. So 2 times r multiplied by the derivative of r, which is dr dt. So we're going to be doing that an awful lot. The derivative of the square of something is 2 times that something multiplied by the derivative of that something. That takes care of the first part of the product rule. The second part of the product rule over here is, well, what's the derivative of h? Well, the derivative of h is just dh dt. Just as a reminder to you, yet again, you want to note the use of the product rule and the chain rule. The chain rule is dr dt and the dh dt that we saw in the previous 2 formulas. So zooming out and taking a look at our next problem, we're supposed to find the indicated derivative of each equation with respect to time h. Letter A is area equals length times width. That's just the area of a rectangle. Let's see what we have here. Job number 1 is to take the derivative of the left and the right, or at least state that we're taking the derivative of the left and the right. So the derivative of a is dA dt. The derivative of LW, well, here we're just saying what is a derivative of LW. We're going to take the derivative of LW. Now looking at LW, that's a product, so we're going to have to use a product rule. Taking the derivative, we're taking L multiplied by the derivative of W. So L multiplied by dw dt plus W multiplied by the derivative of dl dt. That is our product rule. And there's really no more solving to do. It says to solve this in terms of dA dt, and we already have dA dt solved out here on the left, so we're done with this one. Letter B. Letter B is the volume formula, 1/2 BHL. And for this one, we have some very special things to put in here. First of all, we have L equals 10. So that's implying that L is always going to be 10. L is what we would call constant. The other thing we see here is B over H equals 2/5. B over H equals 2 over 5. And finally, the last thing that I see here is dH dt is the thing we're going to be solving for. So I want to get rid of all the variables other than H, if that's possible. So in this main formula here, we see a B, and instead of B, we can turn that in terms of H, because using this ratio, we know that B is equal to 2/5 H. H is H, and this last one, L, well, we know L is 10. So we can substitute both of those quantities in, and lo and behold, we're going to get a formula for V where the only variable is H. And again, that's important for us because we want to figure out an equation for dH dt. So first realization, the base is equal to 2/5 the height. When we substitute 2/5 height for base and L with 10, here's L equals 10. In the formula here, L, we're replacing that with 10. And over here on the formula, we have B equals 2/5 H. So we're replacing this B with 2/5 H over here. That simplifies to 2H squared. And now, being very methodical, we're going to take the derivative of volume, and that's going to be the derivative of 2H squared. So we can think for a minute. 2 is constant, of course, but what's the derivative of H squared? Well, the derivative of anything squared is 2 times the thing multiplied by the derivative of the thing. So it's going to be 2 times H multiplied by the derivative of H. All multiplied out, we get dV dt is 4H dH dt. Last one that we're going to look at for now, letter C. We've got the Pythagorean Theorem, x squared plus y squared equals z squared. We want to solve for dx dt. There's nothing too special for this one. We're just going to take the derivative of the left and the right. And this is that same piece of advice over and over again. The derivative of x squared is 2x dx dt. The derivative of y is 2y dy dt. And the derivative of z squared is 2z dz dt. We can solve that out and get z dz dt minus y dy dt over x. So that takes care of this first page, all of our derivatives. And we can move on to the second part, which is going to be the strategy for solving related rates. Now, if you can take those derivatives, you are on your way home for all of these related rate problems. Rate just means the derivative with respect to time. So let's go over all of these, the 6-part strategy here. Number 1, you got to understand the problem, and you got to identify the variable whose rate you seek, and then the variable whose rates of change you already know. You got to be familiar with all the variables involved in your mathematical model. And for your mathematical model, of course, you want to draw a picture if that's necessary. Label the parts that are important to the problem. And I like this little piece of advice over here. Be sure to distinguish constant quantities from variable quantities, quantities that change over time. Constant quantities can be assigned numerical qualities or numerical values right from the start, which basically means as soon as you start the problem, you can substitute anything that's constant. However, if it's not constant, don't substitute it yet. Wait until the derivatives. Part 3. Write an equation relating the variable whose rates of change you seek with the variables whose rates of change you don't or that you know. Basically, this is usually a geometric formula, but it could come from a scientific application. So this is very well related to the mathematical problem, but the idea here is to reduce down that mathematical model into hopefully just 2 variables. 4 is the derivative part. So you're going to take a derivative. You're going to use implicit differentiation, which is the same thing as the chain rule. And then you're going to substitute values that are variable. And then you're going to interpret your solution. So getting back to our zombie problem, let's take our refresher. Both you and the zombie are 0.1 miles from the intersection. You happen to be east of the intersection. The zombie is north of the intersection. The zombie is heading south at 13 miles an hour, and you are heading east at 9 miles per hour. Let's see what that looks like. Here's a drawing of that. Our zombie is up here at the top, heading south in the downward direction. Here's our zombie, heading south at 9 miles an hour. This distance here is 0.1 miles. So if this zombie is heading south, this quantity, 0.1 miles, that's going to be decreasing. And over here, we're moving east at 13 miles per hour. So if you're moving east, this distance should be increasing. Now that's important for us because if a quantity is decreasing, that means its derivative is negative. And if a quantity is increasing, that means its derivative is going to be positive. So that's going to inform us when we start making some derivatives. Taking some derivatives. All right, here's our model kind of broken down already. This is already solved for z, although you might want to think about how did we get that z. Hint, it's with the Pythagorean Theorem. So you can go ahead and solve that right now. And then the only leg of this triangle which we don't know is the vertical leg. And I always make a point when I'm dealing with right triangles like this one, of using z for the hypotenuse, x for the horizontal leg, and then y for the vertical leg. Labeling this, we know that the vertical leg is 0.1 miles, and it is decreasing at a rate of negative 0.9 miles per hour. Sorry, it's decreasing at a rate of 9 miles per hour. Over here, we're very pointed about making sure that we know that this is positive because x is increasing, and this one is negative because y is decreasing. Part 3, we're going to write an equation relating these 3 segments, and we already have that formula. or that mathematical model, it's right there. Z squared equals x squared plus y squared. And then we need to ask ourselves, are any of those quantities constant? Is x changing? Well, we already know there's a dx dt, so x is changing, so we can't substitute 0.1. Is y changing? Well, we know that dy dt is -9, so that implies that y is changing, so we can't substitute 0.1 for y. How about z? Is z changing? Well, the point of this problem is to solve for dz dt, so that implies that z is also changing, so we can't substitute any values for z. No substitutions can be made because there are no constants. Next part here is to differentiate both sides with respect to time. Let's zoom in a little bit. So we're going to take the derivative of x squared plus y squared and make that equal to the derivative of z squared. Now we've kind of talked about this already. Derivative of x squared is 2 times x multiplied by x prime. The derivative of y squared is 2 times y multiplied by dy dt. And then the derivative of z is 2 times z multiplied by dz dt. You could do a little bit of simplification. All of those 2's can divide out of this, but I don't want to simplify it too much. My advice for you here is don't really simplify until after you've made your substitution. Substituting variables will make the solving the algebra part of this a little bit easier. So just leave this as x dx dt plus y dy dt equals z dz dt. No need to solve yet. The next thing is to substitute any of the variables now. Now that we've taken our derivative, now it's okay to substitute our variables. So let's substitute the things we know. We know x is 0.1. We know y is also 0.1. We know z is at, I think it was 0.14. We also knew dx dt is positive 13. We also know dy dt is -9. And we don't have a value for dz dt. At this point, it's okay to go to algebra mode. You know how to solve this in algebra mode. You're going to do all the multiplications first, and then you're going to divide by 0.141. That gives me that dz dt is 2.828. That's a positive quantity. So that means that the distance z is increasing with time. So the distance between you and the zombie is increasing. Let's go ahead and interpret the solution. When the runner and the zombie are both 0.1 miles from the intersection, the distance between them is it increasing or is it decreasing? And it is increasing. By how much? By 2.82845. Reminder, that's 5 decimal places for everything in calculus. Simplified rules and units here. That's going to be miles per hour. So a few things about this last sentence here is I always like to put increasing and decreasing right over here, and always make this a positive number. So we're always increasing by a positive number or decreasing by a positive number. I don't want to see silly things like increasing by a negative number or decreasing by a negative number, because that's just kind of hard for a lot of people to wrap their brain around. And if you start thinking about it that way, you're bound to get confused at some point. Positive rate means the distance, whatever it is increasing. Negative rate means whatever it is decreasing. That brings us to our important ideas. We've got our 6-point strategy and a couple of other things to think about. Firstly, this is an implicit differentiation or chain rule heavy strategy. We're doing a lot of implicit differentiation. We're using the chain rule an awful lot. Most, or really all, derivatives with related rates are going to be a derivative with respect to t, d dt. And then also importantly, you want to substitute after you make your derivatives. It'll make your life easier. Let's take a look at this. Check your understanding. You have a 15-foot ladder leaning on the side of a vertical wall so that the ladder, the wall, and the ground form a right triangle. The top of the ladder is sliding down the wall at 7.3 feet per second, and the top of the ladder is 4 feet from the ground. Is the area of the triangle increasing or decreasing, and by what rate? So let's try to understand the problem here. We've got a ladder leaning against a wall, kind of like this. The ladder itself is 15 feet in length, so the hypotenuse of that right triangle you see is 15 feet, and that is constant. The ladder isn't getting bigger, the ladder isn't getting smaller, it's staying at 15 feet. The top of the ladder is 4 feet from the ground, and it is actually getting smaller because the ladder is sliding down the ground. This part over here sliding downwards. So we have dy dt equals negative 7.3. Now for the horizontal distance on this ladder, we're going to call that distance x. And using the Pythagorean theorem, we can figure out what x currently is right now. It's going to be just the square root of 15 squared minus 4 squared. Again, that's just a Pythagorean theorem. That gets us square root of 209. Move over just a little bit more. And x is also increasing. But we don't know the rate at which x is increasing. So that's something that we're going to have to figure out. But that's actually not what the question is asking. If we take a look at this question, it's saying we want to know the area of the triangle. Is the area of the triangle increasing or decreasing, and by what rate? So yeah, we're going to actually have to figure out dx dt in order for us to figure that out. Because if we go back to this model over here, we can actually figure out the area. The area is half of xy. And we're going to need an dx dt and a dy dt in order to figure that out. Let's see what we have over here for understanding the problem. Hopefully we've already seen that we're going to have to use two separate formulas, Pythagorean and the triangle area formulas. We're going to use the Pythagorean theorem to find dx dt, the rate at which the bottom leg of the triangle is changing, increasing we should say. And then when we take the derivative of the area formula, that's going to give us the rate of change of the area. So two problems in one over here. We're going to need two mathematical models, and we've already looked at both of them. Here's another look at that triangle. And we're going to have to figure out also d a dt. Okay. So the first thing to do is to write an equation relating the variable whose rate of change we seek with the rate of change we know. Well, from the Pythagorean theorem, we knew that x squared plus y squared equals 225. X is a variable and y is variable. 225 is constant, and that's 15 squared because 15 is constant. And of course, the area of that triangle is 1/2 BH. And we know that the base is x and the height is h. So now that we have those equations, we're going to differentiate both sides implicitly with respect to time. So this is kind of a weird way of doing this problem. We're going to work on both formulas at the same time. If I was going to be doing this in actuality, I'd probably follow the Pythagorean theorem first and then go to the area formula. In fact, why don't we go ahead and do that? Let's do with the Pythagorean theorem first. So let's differentiate both sides. X squared plus y squared equals 225. And that gets us to 2x multiplied by x prime plus 2y multiplied by y prime is equal to 0. Remember that those y primes is equal to dx dt and dy dt, etc. Let's give you a better look here, zoom in a little bit. And then now that we have our derivatives, we're going to substitute into the Pythagorean formula derivatives. And that gives us that x prime is going to be equal to 0.4951. Now that's great because we're going to go backwards and go to the formula for area, which was 1/2 xy. And we're going to take the derivative of that formula now. Now this is a product rule formula, so I'll talk you through it a little bit. The 1/2s, of course, are constant, so we're not going to do anything like that. But this first addend here, we have x. In the second addend, we have x prime. And in the first addend, we have y prime. And second addend, we have y. So it's 1/2 xy prime plus 1/2 y x prime. Next, we're going to substitute the quantities. We have 1/2 our value of x, and this is from the Pythagorean Theorem, and multiplied by y prime, which was negative 7.3. And then we have 1/2 of y, which was given to us, multiplied by x prime, which we just solved for with the derivative of the Pythagorean Theorem. When you crunch those numbers together, you get negative 51777 square feet per second. So that's a negative derivative, and that tells me that the area is decreasing. Let's interpret that solution from that same sentence starter we had earlier in this section. And when the top of the ladder is 4 feet from the ground and the area of the triangle formed by the ladder, the wall, and the floor is decreasing by a rate of 51.777 square feet per second. So that's our first look at related rates. The tips that I've given you about taking the derivative before you substitute any variable quantities, substituting any constant values before the derivative, and then substituting into the derivative before solving. Those 3 tips right there are really going to make these questions a lot easier for you. Hopefully all of this made sense, and that's it for us today, and we'll see you for the next one. Have a good day, everyone.